Hello, and welcome to our online training for students presented by Doable Software. Today we'll be working with our FEA and design software RFEM 6. And the goal of this training is to provide you guys, students, with the fundamental knowledge needed to model/work with any type of basic structure, view results, and understand fundamental basic theories of FEA software. So simple models will be used to help understand these concepts. My name is Alex Bacon, and I will be your trainer for today. I'm a technical support engineer, and I'm joined with my co-organizer, Siska Choa, who is a technical support engineer, and we are located in Philadelphia, PA. I'm just going to hide my camera so the screen is more viewable for you guys. So here's the control panel, and this will be used throughout the training. You can show or hide this panel as well as adjust audio settings. There is a chat box where you can ask us questions as well. Make sure this is set to send to staff only. And this training is intended for you to just listen, but you can model along if you would like to. Some example models I'm not going to go through the modeling process for, so you can download these from the same webpage where you registered for this training. And if you would like to open them up and look at them along with me, you can do so. Cisco will answer easier questions and be my moderator through the chat and save more complex ones for dedicated time before the breaks, where there will be some time before breaks for questions to be answered and discussed. So speaking of breaks, there will be two breaks, 2 5-minute breaks at 2 p.m. and 3 p.m. So if you're in a different time zone, that's just 1 hour and then 2 hours in to the training. The training is from 1 to 4 p.m. Eastern Standard Time. So it is 3 hours long. And here's the content that we will be touching on today throughout the training. So first, we'll start off with some basic principles of FEA just to get the fundamentals understood. And then we'll be going through an introductory example using continuous concrete slabs. Then we'll be going through plate theory and learning about that. And then the second to last topic is nonlinear calculations, and then we'll end today on singularities. So before I get into basic principles of FEA, I would just like to send out a poll and just get a feel for how familiar everyone is with RFM. So I'm going to launch that now. And if you guys could take about a minute to answer that, then I will share the results and we can go over it. Okay, great. So it looks like most of you answered, and 63% of you are beginners. So this is a good course for beginners. That's great. Also average users as well, and 5% on expert. So I think all of you will walk away with at least some new knowledge, helpful tips on how to model. So good. So now let's move on to basic principles of FEA. So to begin, first bit of information to know is that in general, computer programs are based on the displacement method, where the unknown is the displacement. And another method you may be aware of is the force method, where the unknown is the force and the internal forces must be calculated. So with the displacement method, the program will calculate the displacement vectors and then the internal forces and support reactions, for example. So analytical solutions nowadays can be difficult when it comes to large, complicated structures. So, for example, doing hand calculations are almost impossible for some structures, and the limits for what is possible with regards to complicated structures and hand calculating the results are being reached. And so this is where FEA software is required. And so with FEA software, structures are modeled and converted into a finite interconnected element mesh. Materials and cross-section properties are given at each of these FE nodes or finite element nodes. And mechanical behavior is then transferred between these elements. So taking a structure and then submeshing it into finite elements, this is called discretization, this word here. So I believe this is an important vocabulary term to know when it comes to FEA software. Next, we have the FEA calculation workflow. So you can see this in the graphic on the right-hand side. So first, in the first step, we start with the determination of the local element stiffness properties. And then in the second step, the program changes the stiffness properties at each node to the global coordinate system. So element stiffness is composed. Then in the third step, the composition of the entire structure takes place. The fourth step, the boundary conditions and supports are then defined. So these, for example, could consist of sliding, rigid, or hinge supports. And then the fifth step, the displacement vectors can be determined by solving for the system of equations. And lastly, the support forces and then internal forces can be determined just like I mentioned with the displacement method. So now let's do an example to go over. So this example, as you can see, like I talked about, is going to be the continuous plate example. And we're going to go through and model this example and compare results of the bending moment with the continuous beam with our plates here. And we'll go over FE mesh design, convergence behavior, FE mesh size, and result interpretation. So distribution of internal forces, shear stiffness, and result smoothing. So now let's jump into RFEM. I'm going to move over to RFEM now. And so first, let me just explain what RFEM is. So RFEM is a structural analysis software that's capable of analyzing elements such as plates, members, and solids. And so then deformation, stresses, and internal forces can be calculated on these 3D structures or 2D structures. And almost anything is possible to calculate, including properties like volume. So with this, you can see I have a model already opened up. We're just going to be going over the UI of this already modeled structure and just the UI of RFEM itself, since it seems like most of you are beginners, and we'll just touch base. So on the left-hand side here of the program, we have the navigator panel, and this panel is very important. This is where all of the model data is organized. So you can see I have my model opened here, and all of these categories that have arrows next to them contain model data. So this is an easy place for you to check and see what's included in your model. Then down here at the bottom, we have the tables. And so just like the navigator panel, down here you can view and also edit these tables using numerical input. So I could, for example, under structure, basic objects, and node tab here, I could add in some nodes or delete some nodes if I would like to. You can see we have multiple tabs here for organizing elements under the basic objects such as materials and sections, and you can add and delete information down here. Also, we won't be going over any design add-ons today, but the design add-ons are also located normally in this drop-down if you're using design add-ons. You can see I have a white background here. If you would like to change the theme of the program or the background color, you can go up here to Options and Display Properties. And then down here at the bottom, there is a default drop-down, and you can choose between loading in a dark background or a white background. So then, next bit of information is here we have the work window. And so with this work window, you can see we have the graphical view of our model, and you can manipulate this model using the scroll wheel on the mouse. So clicking in the scroll wheel allows you to move the model in translation. Holding Control and clicking in the scroll wheel allows you to rotate the model. And then, of course, scrolling in and out with the scroll wheel allows you to zoom in and out of the model. Up at the top here is our toolbar, and this is filled with all of the necessary tools we would need to model graphically. Also, you can see, or should see, that this is all organized into categories, and you can move these bars around here and customize this to the way you like it. Or if you just wanted to look the way mine does right now, you can right-click in any of this open space here and hit the restore to default layout, and this will organize your tools like how it looks for mine. Then up at the top here, we have the insert menu, and this is helpful if you can't find the tools you're looking for in the toolbar. So you can go to insert, and then you can locate the tool you're looking for as it's organized in these arrow menus. You can change the view of the model in the toolbar up here using these buttons to manipulate the view. So you can use those to change the view. There's also a default isometric view. You can change the rendering here from wired frame model to solid model to transparent model. Next, we have the display tab down here at the bottom. So under the display tab, you can turn on or off the graphical rendering of objects and other settings. And so turning off and on the render of something just turns off the rendering, and it will still be considered within the calculation even though you can't see it in the work window. The next tab is the Views tab down here in the panel. And so we can activate visibilities, for example, and you can see I have members and cross sections of just this type checked on. So now anything with this cross section will be shown, and anything else will disappear in the background. And you can also create user-defined views. So let's say I want this to be a view that I want to see a lot, so I can click on this button and I can just name it something random. And now if I want to see this custom view, I can just simply click on the button here, and then I'll see that view pretty easily. So we can turn off visibilities, and then if I turn on, I've already run the results for this model. So if I turn the results on, I will have the fourth tab here, which is the results tab pop up. And in the panel is where I can turn on or off the results I would like to view. So you can see I can turn off the results from my member, and I can turn on the results, the global deformations. And so you can view your global deformations by checking that box. You can view the results on your member, for example, and view internal forces such as moments, axial forces, and shear. And then you can do the same for the surfaces. We'll be going through this more in detail later. And that's the gist of viewing the results. And one other thing I wanted to mention before we move on is highlighting. So if you drag from left to right, anything within the box that's engulfed in the box will be selected. And then if you drag from right to left, anything touching the box will be selected. So that is how highlighting works. And with that said, so that's an overview of RFM 6. And now we can move on to creating our continuous plate. But before that, I would like to give a test of some questions. So first question should pop up soon for you. And then once we go through these two questions, then we can move on. So I'll give everyone about half a minute to a minute to answer that. And yeah. Okay, so the question is, or was, what is the definition of discretization? And the correct answer is what looks like most of you got correct, is a structure that is converted into finite elements. So good job. The other answers were the calculation of a structure according to FEA and the submeshing of finite elements into smaller elements. The second option I could see, but that one's not as correct as the first option. So I'm going to hide that. And then I just have one more question before we move on. And that is, what is RFM? All right, so let's take a look at the answers. So what is RFM? A 3D structural frame analysis program, a 3D FEA program for calculating members, plates, and shells, and a 3D FEA program only for calculating members. So the correct answer is the second option, which 64% of you got, which is great. The first and last one are incorrect because it's not only just a program for calculating frames and members. So great. We can move on. So I'm going to hide that. And so now let's move on with modeling our continuous plate. So the first thing we want to do to create our model, if we're creating one from scratch, is to go up here to the left-hand corner and click on this button here, create a new file. or create new model. And then the model name, we can just name this continuous plate. And I'm just going to put training after it, 3. And so, yeah, this is where we can enter in the model name. And then here you can enter in a model description if you would like, but this isn't necessary. Then down here we have the type of model. So we can either choose 3D or we can choose to model a 2D model. You can see here there's a difference between plate and 3D. We're going to choose 2D plate in the XY plane. And what this does is it keeps any forces and locks the model within the 2D plane and prevents any rotation or in/out of plane forces to happen, so we don't have to worry about supporting certain directions. Whereas with the 3D option here, we can get in and out of plane rotation and forces. So we're going to create a 2D model in the XY plane. There's also the 1D options as well. We have options. You can use the project manager feature here, and then we have the initialization of a new model. So this is if you wanted to use templates, and then you can turn on and off elements such as surfaces and members. You can see solids are grayed out because we're using a 2D model. Next tab here is we have the add-ons tab. And here's where you would activate design add-ons. If we were using them today, we would activate some of them. For example, concrete and steel are here, but we're not going to be utilizing these in this training. I'm also going to turn off the standards for classification and wizards, as we're not going to be modeling according to any standard or creating load cases and combinations per any standard. So we can turn these options off, which means we can skip through standards 1 and 2 tabs up here. Under the settings and options tab, we can choose the orientation of our global axes. So of our global Z axes, I'm going to keep this set to upward. And then also for our local axes, which is denoted using lowercase x, y, and z throughout the program. And that's for our surfaces and members. We're going to keep this set to upward as well. And then model tolerances and these other settings we can leave as default. Also to mention, I'm going to be using imperial units throughout this training. You can change between or switch between imperial metric units by going down here to this button and clicking on units and decimal places. And then you can go down here to load, save template, and change the default units you have set, and you can change between units as well here. So like I said, I'm going to keep mine in imperial units, click OK, and then this should open up a blank model. So now we can edit the grid points and units. So first you'll see in the blank model that our grid has been created here. It's a blank grid, and we have our grid points here. And right now, by default, if I go up here to the button settings of work plane, grids/snap settings, if I click on this, you can see I have mine set to a default of 50 by 50 grid points with a spacing of 1 foot by 1 foot. And what we want to do is change this to 100 grid points by 100 grid points, and each in the negative and positive direction. So you can enter those in. I have also created, you can save templates. So I saved this as a template, and we can go to load template. And you can see I saved this as a template called student training. And you can see you can set different templates as the default if you're using the same settings over and over again. So if I click OK, you can see that my template was loaded in, and I have 100 grid points by 100 grid points with a spacing of 1 foot by 1 foot. So now if I click OK, you'll see that my grid here was increased by 50 grid points. And so now we can get into modeling our concrete slab. And so the first thing we want to do is go up here to the new rectangular surface. And with this tool, we can use this to, like it says, create a new rectangular surface. And this surface is going to be sorry about that. The surface is going to have a material and thickness. So every surface in RFEM has to have a thickness and a material set to it. You can see you can choose a stiffness type for the surface. We're going to stick with standard today, but we do have rigid and membrane and low transfer. So first, we're going to create a new thickness using this button here. So we're going to hit create thickness. And this thickness is going to be uniform. And every surface thickness has to have a material set to it. And so I'm going to click on this button here to import a material in from the material library. So I filter to the United States, concrete, and the ACI 31819. I'm going to choose concrete with a compression strength of 4,000 psi. Click OK. And now I just need to enter in a thickness, and that's going to be 12 inches. Also, we can edit our material. So I'm going to click the edit material of the thickness button here. And then I'm going to choose to create this or set this material to user-defined materials so that we can edit our basic material properties here on the right hand. And so I'm going to change the Poisson's ratio from 0.2 to just 0. And so this will allow us to get equal distribution of results across our surface. Normally you wouldn't do this, but I'm just going to do this for example purposes today, and click OK. And so now I have my material and thickness set, so I can click OK. And now you can see those are set here. And so now I'm going to click OK. And you can see my cursor has changed to this reticle. And so I just need to tell the program or give the program 2 points on where this rectangular surface is going to be. The first point is going to be at the origin. And then the second point is going to be at 32 feet in the X direction and 16 feet in the Y direction. Click OK or left click. And now you can see our surface has been drawn. So I'm going to right click. And now you can see our rectangular surface has been created. So now the next thing we want to do is add supports into this surface. We're going to be using line supports, and I want to have a line support halfway down my surface. So I'm going to first have to draw a new line. And so I'm going to snap to the midpoint of the line up here, and then snap to the midpoint of my bottom line. And so now you can see we have a middle line here. And you can also maybe now notice if I zoom in, we have different colored nodes. So these nodes here are red, and then these nodes that I just drew are blue. And the reason these nodes are blue here is because if I double click on one of them and I go to the main tab, you can see that the node type is set to online. And what this means is under the online tab, we can see that the node is integrated with line 4 here. So if I right click and I turn on numbering, you can see that we have line number 4 here. And if I double click on line number 4, then we can also see under line number 4 under nodes online that node 6 is located on this line. So you don't have to worry about this, but in the background, that's what RFEM is doing. And that's the reason why this node here is blue. And this node here is red because it's a standard node and just defining the line itself. So good thing to keep in mind. And so now what we want to do is edit this line over here. So we can double click on it to edit it. And then we can, under editing the line, we want to add some supports to this line. So we can click on support. And then under the support tab, we can go down to the drop down here and we can choose this default or predefined support. That's a hinge support, and click on it and then click OK. And now you can see that our line here now has our hinged line supports on it. So what this means is that this support will support translational degrees of freedom in each 3 directions, but the rotation is released for rotation about each of these axes. So now we want to add some support to our midspan here. And what we can do is we can highlight just our line here. And we also want to add support to our other side here. So I can hold Control and also highlight that line. And then we can go up here to the toolbar and hit Assign Line Support. And instead of just using the predefined support, we can also click on Create New Line Support. RFEM will remember the selection of the lines that we selected before going into the tool, which you can see here in the graphic. And for this, we want to choose the sliding in the X direction. So you can see it unlocks the X translational degree of freedom and then locks the rotation about the Z axis. And you can also see the symbol for the support has changed. And if we click OK, and then click OK again, you'll see those supports have been added. And you can also see when clicking on elements, what elements they're tied to. So you can see our support is tied to line number 3, which is defined by nodes 3 and 4. So it's easy to see how objects are connected within RFEM if you need to know that. So when we created this model, we already had a load case that was created automatically. And so if I go up here, you can see under this dropdown, it's called self-weight, LC1, and I can edit this load case by clicking on Edit Active Load Case. And you can see that we have self-weight activated for this load case. I'm just going to turn self-weight off. And we only need to worry about one load case, which is good. And we're going to be adding some loading to this plate now. And every loading requires a load case to be assigned with it. So now that we have our load case created, we want to go up here to the tool new surface load. And under the new surface load, you'll see, clicking on that, you'll see this dialog box will pop up. And here we can set our load type to force and then uniform. And we can set our load direction to global and the Z axes on true area. And then the load magnitude will be set to negative 0.21, which is 210 pounds per square foot. And yeah, we can click OK. And now all we need to do is choose our surface graphically. And now we have our load here graphically placed onto our slab. You can also right-click on this load and you can decrease the size of it graphically if you'd like so. And so yeah, now we have our loading. We also want to now get into FE mesh refinement. So I can go up here and turn off, well, I'll keep my loading on, but we can go up here to this button here and click on the drop down and then take a look at the mesh settings. So here you can see by default, the mesh that will be generated is 1 foot. The final elements are 1 foot by 1 foot. And so if nothing changes, this is what we're going to generate. But what we want to do is add in an FE mesh refinement to our surface here. And to do this, we can go to the navigator panel on the left-hand side, go to the data tab. And then under the data tab, we can go to the types for surfaces and then surface mesh refinements. And then we can go to new surface mesh refinement. And we want to make 3 of these. So we can go down here and click on create new surface mesh refinement. So now we have 4 of them. And this first one, we want to make the FE length set to 7 foot. The second one will be set to 4 feet. The third refinement will be set to 1.25. And then the fourth refinement, we'll set it to 0.4. And so now if I click OK and I expand my surface mesh refinements, we can see that we created them, but they're this light blue color because they're not assigned to any surface. And so we'll just leave this as B for now. And what we want to do next is make some copies of our surface here. And so I'm just going to highlight the whole thing with the loading and everything and go up here to the tool move/copy selected objects. I'm going to create a copy and I want to make 3 copies in the X direction, and I want each of these copies to be displaced by a vector of 37 feet. And so now with this set, I can click OK. And you can see now I have 3 copies of my plates. And what I want to do is take this and just move it over so it's more centered in my grid. And now we have our 4 plates. And so now with our 4 plates, we want to create a new single member. But I would also just like to send out a poll, just make sure the pacing is okay. So I'm going to do that now. So if everyone could let me know, that'd be great. All right, so I'm gonna close that and share the results. So it looks like the pacing's okay for most people, but a lot of you are asking to slow down, so I can do that. So I'm going to hide the poll and try to slow down a little bit. Yeah, so next thing we want to do, now that we have our plates modeled here, is create a new member or create our beam. So I'm going to go up here to new single member. And now, so clicking on this button up here, new single member, this will allow me to create a member and draw it graphically. And so under the new member dialog box here, and under the main tab, we have our member type set to beam. You can see we have other member types here. I'll be going over these in a little bit. But beam just means that the member can take both tension and compression forces, and the connections are fully rigid. And so then we just want to move to the section tab. And here's where we want to set our cross section. And we can set our cross section using this button here, import from section library. And so I'm going to click on that. And here you can see our section library. So we have all of our sections organized into these categories here. I just want to go to massive and choose a massive rectangular section. And then under this dialog box, we have some settings for our cross section. And so we want to set the material. You can see I have a couple materials already predefined here, but if you need to, you can use the material library to import new materials in. And I would want to choose concrete 4000 psi, for example, just to simulate our plates. And then under the parametric massive tab here, we would want to choose a depth of 12 inches and then a base of 20 inches here. And so this is going to simulate the same thickness as our plates. And then under the main tab, we can leave all of this set the same. Click OK. And now you can see our section appears here. And you can also click on this button to display section details. And you can view your section properties here if you'd like. And so now with all of that defined, we can click OK. And then now I just want to snap to my grid points and draw this section 5 feet away from my plates. So I'm going to snap to this grid point. And then I'm going to, I can either just draw out the length of my section, or I can keep my mouse going in the direction I would like the member to go. And then on my keyboard, I can type in the distance 32 feet, which you'll see will change in the dialog box up there on the left. And then if I hit enter and then right click, I can exit out of the tool and you can see my beam here has been drawn out. And so now we need to add some supports to this beam. I'm going to turn off the showing of my grid. You can see we have some buttons down here at the bottom. And I'm going to turn off the grid here. Also, one thing I forgot to mention in the beginning of this training, it will be recorded. So if you're trying to follow along and you're falling behind and you can't catch up, you can always, we'll be sending out the recording of this training and you can always watch it back later. So yeah, so we want to divide this member by right-clicking on it, and then under members, and we can divide the member by going to divide member, and you can see we have, you can see we have some options here to divide the member. I'm going to choose by a number of intermediate nodes. I'm going to choose one intermediate node to divide it by. And then I'm going to choose the option create on member nodes without dividing member. And so what this will do is it'll add a node to the member without dividing it. I'm going to click OK. And it might be hard to see, but you can see node 27 here is now at the direct center of our member here. And now what I can do is I can add some nodes or some nodal supports to my nodes here. And so we want to go up to the button assign nodal support. And this first nodal support is just going to be a simple hinged support. And I'm actually going to edit this support because we want to restrict rotation about the x-axis, like so. And the reason for this is because when you have just a single span member here, you need to make sure that it isn't allowed to rotate about its local x-axis freely, or there will be an instability in the program. Now we can add in our two other supports here. And so I'm going to create a new nodal support, and it's going to be sliding. So we're going to choose rolling in the x direction. Click OK, click OK again. And then we can graphically select our nodes here to add those supports to. And now you can see we have our supports added. Now we need to add some loading to this member. So we want to use the tool up here, new member load. There's also the tool new line load, and when it comes to both of these, there's a good rule of thumb is line loads are only supposed to be applied to lines, so like lines that are boundary lines surrounding or defining a surface, and member loads should be applied to members. So we're going to choose member load, and this load's going to be in the negative direction, just like the surface load, and it's going to be 210 pounds per foot, or 0.21 kip per feet. And so then we're going to have a force. It's going to be uniform in the z direction. And so that we can click OK, and graphically select our member, click OK again. And now we have our loading assigned to our member. And so now all of our elements here are loaded and supported. I can go up here to the show loads button and turn this off. And now we need to add in our surface mesh refinements, which we didn't define. So I'm going to do that now. So we can right click on one of them and go to edit, or we can click on assign to surfaces graphically. So I'm going to click that and assign my 7-foot refinement to the first surface here. Then I'm going to right click on 4 feet, assign that to my second surface, assign the third refinement to the third surface, and then assign my fourth refinement to my fourth surface. And so now I'm going to change the model to a wireframe view by clicking on the button, the rendering button up here. And then I'm going to generate the FE mesh. And I'm going to do that by going up here to this button and hitting the drop down and hitting generate FE mesh. Normally this is done before the calculation is ran, so you don't have to worry about it, but for example purposes, I just wanted to show you what the FE mesh for each of these surfaces looks like now. So focusing on this first surface, that was our 7-foot FE mesh refinement, you can see the quality of this one is really bad. So definitely expect inaccurate results when it comes to the quality of this one. You can see how it gets better as we move on to the second surface here, and better. And then our fourth surface here looks the best. So I would expect extremely accurate results from this one. And yeah, so that's what our FE mesh looks like right now for our surfaces. And now we want to add in a results section to our surfaces. So I'm going to click on the button up here, results sections. And you can see here we have our results section. So the main thing we need to do is just tell the program what the first and second point is, the projection direction, which is going to be the global z direction, and then we want to show section in the local positive z direction, which you can see what it will look like on our surface here. And then we can use this button here to select 2 points graphically. So I'm going to select the midspan in the beginning of the first surface here, and then drag it all the way to the midspan of the fourth surface. You can see you can add a edit the section name. I'm just going to keep it as section 1, and then assign this to all surfaces. Click OK. And now you can see we have our section created. Other thing I wanted to note is when you create an FE mesh refinement, you can see that symbol located on the element that you assigned it to. And you can see the symbol is larger, or the size of the symbol depends on the size of the refinement that you added. So it's a little tidbit to know. So now let's calculate the results. So all I need to do is go up here to calculate all results, this button here, which looks like a little abacus. And then all of the results will be run. And you can see right now our fourth tab here in the results has been added. And we are now looking at the global deformations. And I always recommend checking the global deformations as the first thing to look at, because you can always tell if there's something wrong with the modeling if your global deformations look strange. So you can see our deformations look pretty normal. They all look good. So that's good. Nothing was modeled incorrectly. Good visible check. I'm going to deactivate the results or result sections, so we can turn off the result sections if we want by unchecking this box here in the navigator. We can also take a look at the internal forces. So let's do that. I'm just going to highlight our last surface here and our beam. And then what I can do is go up here to this button, hit the drop down and choose visibility by selected objects. You'll see any object that wasn't selected was grayed out. I can even right click and turn off show hidden objects in the background. So now we have an even cleaner look. And we can turn on internal forces of our member here, which will turn off global deformations. And then we can turn on so if I turn on the results for members, then under the internal forces here, obviously we're not going to have any axial forces because we just have a beam here. So we would want to look at the moments, and you can see I chose M and Y, which is the moments, the moment about the local x-axis, which if you right click on the member, you can turn on the local axis system of members, and you can see what that looks like. So these are the moments about our, local y-axis. I'm not sure if I said x, I meant y. And then we can also take a look at the results on our surface. So what I'm about to show you is pretty important. So to see the results on the surface as well, that's a little different. We can just check on the box surfaces here. And then under internal forces, similar to the member, we can go down to internal forces. And if we wanted to compare results between the two, we would want to turn on or show the moments along the x-axis. So these are the moments. This is the moment in the surface along the x-axis, and this is comparable to the moments about the y-axis for the member. And so yeah, that's how we can look at the internal forces. We could also take a look at the shear, so Vx along the local x-axis of the surface. And you can even turn on the axis system of the surface as well. the local x-axis system so we can see that. And then we could turn on the shear VZ, which is in the local Z direction for the shear of our member here. And so, yeah, that's how we could compare the two. And so now let's clear our results, clear our visibility. So I'm going to go up here to this button and cancel this visibility mode. And so that'll bring back the rest of our surfaces. And so now what we want to do is activate the results sections. So I'm just going to zoom out here. And so what we want to do is turn on our results sections again. And so now you can see a better comparison between those two. And we also want to turn on the local extremes for our results sections, which is under the values of, under the results sections down here. So this separate panel down here is for changing how the results look graphically. And if we go into results sections, I could turn on local extremes here. And now we can see the values of the local extremes of each of our elements here. And so now if we take a closer look at something like bending moments, we can see how the results compare between the beam here and our plate here. So obviously the surfaces should match the beam, and this shows how important it is to make sure your FE mesh is fine enough, because you can see the super fine FE mesh here is the closest comparison. So our maximum moment at 6.70 and 6.70. And then you can see as we move down the line here and our FE mesh gets worse, our results start to stray further and further from our control of the beam control. So the finer the mesh gets, the more points of, well, results are only being calculated at each FE mesh point or node on the first surface here. And so the finer the mesh gets, the more points of data we have, and then the more accurate results. So keep this in mind, or keep in mind though, if your mesh is too fine, your calculation time will increase. And so you want your mesh as fine as necessary, but as coarse as possible. And so what I would recommend is something like the third example here, the mesh in the third example here. And a good rule of thumb is to have at least 4 FE mesh blocks between any given span or boundary. So this second surface here would be the minimum of what I would recommend. And so next we can take a look at the result diagram of our section cut here, which is pretty interesting. So we can get a better view of our result diagram starting from surface 1 all the way to surface 4. And it's interesting just to see how we have very little points of data for the first surface, which looks very inaccurate, and how this gets smoother and smoother as our FE mesh starts to increase and look a lot better. So this is a good stopping point before we take our break at 2 o'clock. I'm going to switch back to the PowerPoint. And if there's any questions, Siska, any complex ones that I can answer.
Hi, Alex. Yeah, we just have one question.
Okay.
Can you show us how to create a user-defined material?
Okay, yeah, that's a good question. So I can switch back to RFEM to show this. So if you want to create a user-defined material, you can go here to the data tab under the navigator. And then you can see here we have our materials, which these are the ones we pulled from the material database, and I can right-click on the materials here and click on New Material. And then instead of importing a material in from the material library, we can choose the option here, user-defined material. And then you can see here we can just enter in our material properties manually. So that should answer the question, I think.
Yes, and that's all the questions I have for you.
Okay, awesome.
Thank
Thanks,
you.
Jessica. Yeah. So with that said, we can take our 5-minute break and we can return here at 2:05. All right, so we can resume now. I'm going to go back to RFEM. My sniffling, please. My allergies have decided not to cooperate with me today, so sorry about that. And yeah, so RFEM, we can now talk about shear stiffness. So with shear stiffness, when it comes to hand calculations, if you're trying to, let's say, for example, do hand calculations to match the results of the beam here, you have to take into account shear stiffness effects. So taking into account shear stiffness, this is what RFEM does in the program. And what this does is it leads to an increased deformations due to shear forces. And this is something that is not taken into consideration with hand calculations. With hand calculations, you assume that a beam like this has infinite shear stiffness. And so this plays a major role when it comes to a material like concrete as well. So this is taken into account, like I said, by default in RFEM, and you can deactivate this so your hand calculations match. So if I wanted to deactivate shear stiffness and not take it into account, for example, with this beam, I could double click and edit the beam. And then you would want to go under the section tab here and then go under and edit the section. And then under the options for the section, you can deactivate the shear stiffness. And so checking that on, I'm going to click OK. It's going to ask me, it's going to tell me that these actions are changing the results, and the results are going to need to be recalculated. Do you want to continue? Yes. Click OK. And so now we just have to rerun our results, and now we can see how the results deviate from our previous results. So now you can see something like our member bending moments have now increased to 7.2. Before they were closer to 7.0. And so that is what happens when you take into account or don't take into account shear stiffness. And this is the results you should see if you're doing hand calculations. So now I'd just like to give another test and see what everyone thinks. So this next test is going to come up now. So I'm going to launch that and give you guys a little bit to answer that. All right, so let's take a look at the results. So the statement is the FE mesh size should be, and the first option is as fine as necessary and as coarse as possible, then as coarse as necessary and as fine as possible, and the last option is as precise as possible and as coarse as necessary. Now this is a little bit of a brain teaser, but the first option is the correct option, which is as fine as necessary and as coarse as possible. So the reason for this is you want it as fine as necessary. You don't want your mesh super small, because then that'll increase your calculation time. And so that's why you want it as coarse as possible, so your calculation time isn't as long, but you want it as fine as necessary so that the results are accurate. So the first option was the correct one. So I'm going to hide that. Now we can move back into RFEM. And so Actually, we want to move back into the PowerPoint so we can go over and discuss and talk about plate theory. So plate theory, to help understand plate theory, I'm going to use some beam theories as an analogy. And one of the beam theories is Bernoulli's theory, which comes with these assumptions. So the first assumption is that the cross sections remain in plane and perpendicular to the member axes. So there's no warping. And then the second assumption is that there's no consideration of shear deformations and that the shear stiffness is completely rigid. And then the second theory is the Timoshenko theory. And the assumptions with this one is that the cross sections remain in plane, but they don't remain perpendicular to the member axes. And so this means that shear deformations are taken into consideration and the shear stiffness is limited and isn't completely rigid. So the Timoshenko theory takes into consideration shear deformations where the Bernoulli theory does not. And here is a graphic. So you can see with Bernoulli's theory that the cross-section remains completely perpendicular to the member axes. So we don't have, that's how the deformation, you can see, remains perpendicular to the member axes. And then with the Timoshenko theory, here we have an increased angle. So this will lead to additional deformation, and due to additional deformation, shear deformations, or this will lead to additional shear deformations and shear stiffness. And so the reason for this is because we consider shear stiffness. Now, how do these compare to the equivalents of the two plate theories for plate elements? So Bernoulli's can be comparable to the Kirchhoff plate theory, and the assumptions when it comes to the Kirchhoff plate theory is that we assume we're going to be using a geometrically linear analysis, so small deformations. We're going to be using a linear elastic material basing off of Hooke's law. The cross-section remains flat. There's no warping. There's constant thickness, and there is no consideration of shear deformations. And then, similar to the Timoshenko theory, is we have the Risner-Milne theory, which works the same for plates. Here, we're making the assumption that basically the same assumptions as the Kirchhoff theory. These first four assumptions are the same. But what's different is we do not take into consideration we consider shear deformations, and we also take into consideration transverse/lateral strains for this theory. So you can see here, Kirchhoff theory, we don't consider shear deformations, and the Risner-Milne theory, we do. So here's a graphic to get a better understanding of transverse/lateral strains. So we have a beam here, and when a tension force is applied to it along its length, the cross section will shrink, and this will be with regards to or respect to the height and width. And you can see the shrunken cross section in the red here. And the factors mu and epsilon x take this into account for both the base and the height. And so just to summarize, the Kirchhoff theory here, when these results, when used with very thin plates, are great. And this theory does not consider shear deformations. And you also have to keep in mind that this only considers pure bending and load bearing capacity. And this is a very simplified approach. Whereas with the Risner-Milne theory, this theory is great for the use of thick and thin plates. And the reason for this is because we do consider shear deformations, and you have to take into consideration that the shear influence component is relatively high. If you're neglecting shear forces, you're going to have a significant error. And this is a high value approach and increases the accuracy of your shear forces. So in my opinion, the Resner-Mindlin theory is what you should be using all the time, but it's just good to know the difference between these two theories. And now to relate this back to RFEM, we can look and see where these settings to choose between these two theories are located. So we want to go under the navigator and under the data panel here. And then we want to go under the static analysis settings. And we would want to go under the settings that we're using. So we'll edit the static analysis settings. And you can see we're using the geometrically linear analysis, which is for our load cases. And all load cases are calculated using a geometrically linear calculation by default. And then under the basic settings, you can see here we can change our bending theory from Mindlin to Kirchhoff if we want, and click OK. And we should see a difference in our results. So we do. You can see now our results match better, more closely to our beam here. And this is because both of these are now not taking into consideration shear deformations. Now we would have a bigger delta in our results if we were using a thicker plate, such as a foundation plate. And yeah, also the shear forces and deformations are going to be changed as well. So now the question I would like to pose next is a true and false statement. And I'm going to launch that now. All right, so it looks like most of you voted or answered. And so the question or statement is the Kirchhoff plate theory does not consider shear deformations, and this statement is true. So it looks like most of you got that correct, which is good. So yeah, so the Kirchhoff plate theory does not consider shear deformations. It's more of a simplified approach. Okay, so hide that. And now we want to go back to the PowerPoint. And I'm going to go over nonlinear calculations. So when it comes to nonlinear calculations, there are some disadvantages. One of the disadvantages to using a nonlinear calculation is that the superposition law is no longer valid or can be used. So for example, if you're running a second order calculation, such as for load cases or combinations, that would include P delta and big P delta and little P delta effects, you wouldn't be able to add those load cases or combinations together because it is a nonlinear calculation. The program would give you an error if you did that. And so typical application areas in RFEM 6 include geometrically nonlinear calculations, such as second order analysis, which includes behavior such as big P delta and little P delta effects, what I just talked about. And then this also includes nonlinear material behavior. And so to help understand nonlinear materials, so you might remember if you've done this in lab yet or not, is some you might have done some tests on some steel specimens, and you might have been testing the yield strength. And if you remember, the stress and strain graph for the yield strength of a steel is normally linear. And so there is the elastic region, which is a linear region, and then after the steel has yielded, then you would get into the plastic region, which is not linear. And some examples of nonlinear materials would be such as glass or silicone or cables. And then we also have nonlinear behaviors for structural objects like members, hinges, and supports, for example. So I'll be showing examples of all three of these areas in RFEM 6 after this. Also, keep in mind that these types of calculations increase accuracy, so this is an advantage, as the accuracy is increased, but another disadvantage is that the calculation time can also increase when it comes to adding nonlinearities. So now let's go back to RFEM and go through some examples. So I'm going to open a previously modeled model. Sorry about that. So I'm going to open a previously modeled model by going up here to the Open Model button. And I have set up a frame with tension-only members, which I'm about to show you now. So actually, I have this opened already. So if I open this up, here is a frame. And this frame is set up with tension-only members here. And these members are bracing this frame. There are lateral bracing in the X direction. And we're also just assuming this frame has been taken from another structure. So imagine the top here is framing into a roof. And so these supports are just supporting it in plane and out of plane. And so this wall would need bracing in the global X direction, like I just mentioned, and that's what our X bracing here is. And you can see this X bracing, if I double click on it, is set to truss, so tension only. So let's see what happens if I highlight this X bracing and delete it. If I try to run my calculation here, also just to mention I have loading pushing on this as our wind in this direction. So if I try to run my results here, I'm going to get an error. And this is telling me, if I click OK, that the stiffness matrix is singular. And so we have an instability, is what this is telling me. And what the program is doing is checking the stiffness matrix. And if there is a singularity, then that means the structure is unstable. And you can see this says the structure is unstable here in this error because we have no bracing in the X direction. This whole thing is able to just fall over. So what we need to do is stabilize it by adding bracing. So I'm going to show you how to add bracing back in. And so I'm going to go up to new member, and then under new member here, I'm going to choose the member type truss. And it says only axial forces. And so this truss member can only take axial forces. It cannot transfer shear or bending moments. And so what we want to do then is also check on the nonlinearity option here. And so then you'll see this nonlinearity tab will pop up. And I want to create a new nonlinearity and set this to failure if compression. And so what this will do is it means that this member takes any compression loads then the member will fail. And so we're assuming these are cable-like elements and can't take compression. You can also see we have other types here, such as slippage, failure of tension, and then some other options. So we'll click OK. And then we'll go back to the main tab and click OK again. And now we can simply just draw in our bracing here from node to node by just left clicking. And I also just realized I forgot to change the cross section. That's fine. We're just going to continue drawing these. Oops. Not sure what happened there. All right, just restart the program real quick. Sorry about that. That was strange. So sometimes you might get, can happen every once in a while, but the program might force close. And I'm just going to, there we go. And the good thing is that if you forget to save, that the program automatically keeps backups of all of your models. So I'm just going to go through and restore these real quick. Shouldn't take too much longer. We can get right back into it. Okay, there we go. All right, so back to drawing the section here. I'm going to delete this one and we're going to create a new member, set this to truss only, nonlinearity, failure of compression, section. So I forgot to choose the section last time. We're going to change this to round, 0.75 inch diameter, click OK. And so now we can draw our members here, or our X bracing. We can draw that out, and then we can highlight it, and we can hold Control and take this and hold Control and make a copy of it. Oops, try that one more time. So you can highlight things, hold Control, and then drag and drop them to make a copy of them. And so now we have our tension only truss members here. And now if we run our results, we get no error. If we take a look at our global deformations here, you can see that only our X bracing here, member, and tension is giving us results, whereas our tension only members here have received compression forces and have been deactivated, so they're no longer in the calculation. We're adding stiffness to the structure. If we turn on members and turn on our internal forces and look at our axial forces, or you can see only the members that have tension forces are showing results, whereas our members that have compression in them have failed and are not showing axial forces. So now we can move on to the next example. And this model, if you are opening these models with me, is called reactivation of tension members, model number 3. And so for this example, I'm going to show you that sometimes a structure cannot handle the loading applied to it, even if it's stiff enough. It could be stiff enough, but it may not be able to handle the loading, and it might be unstable. So you can see here we have a frame, and if I turn on the loading, you can see this frame just has these nodal loads adding compression to our columns here. And you can see we have a trust member up at the top here. And again, a trust member cannot, a normal trust member cannot transfer moments at the connection points. It can only transfer shear and axial forces. And you can also see we have tension only members here for our X bracing. So these are nonlinear members and can only take tension forces. And so let's see what happens when we run the results. And you'll see when we run our results, you would expect this structure to be fine and totally stable. But the reason it's failing is because when these compression forces activate, they shorten the columns here, and which this causes our tension only members to take on compression in the first iteration, and so then the structure fails. And so this is the reason why we're getting instability for this structure, because once this X bracing fails, the whole structure or this frame here is unstable in the Y direction, which you can see here down in the warning that the structure is unstable in the Y direction and the stiffness matrix is singular. So how can we avoid this? You would think the structure should be fine. Well, there is a setting for this. If we go under the static analysis settings, or we can even just go up here and edit our load case. And then you can see we're running this load case according to a second order analysis. If we click edit here, we can edit the settings for the second order analysis. And you'll see, since we have a nonlinear elements, we have this tab here called reactivation. And under reactivation, we have an option here called exceptional handling. And what this does is, after the first iteration, RFEM will not remove the tension members experiencing compression forces all at once. It will remove these members each iteration step by step. So the failing members are removed by one in each iteration. So that's what this option here is for. Okay. And so turning that on, let's see if our calculation runs now. So we can hit calculate. And now you can see that our calculation runs now. So this is how we can take into account nonlinear members for a structure that may be stiff enough and you would expect to be stable. And you can see that that option allows us to now run the results for the structure. You can see this member is fully deactivated when this member is taking tension forces and supporting our structure in the X direction. So the next example we can move on to is the nonlinear support example here, model number 4. And so in this example, I'm going to show you can assign nonlinear supports to a structure. So on the left-hand side here, we have a cantilever with a rigid support at the bottom and a green nodal support here. And the cantilever on the right-hand side has a blue nodal support. So whenever you see an element that's blue like this, when usually it's green, that means it's a nonlinear component. And so I can edit this nodal support to show you the nonlinear option that's activated. So I can double click on it and then click edit nodal support. And you can see here that in the translational X direction, we've chosen this nonlinear option here, which is failure if negative px. And that means if this node here experiences a negative force on it, then it will fail. So we can see that if we click OK again, and I turn on my loading, you can see that I added the same loads here to each side. And if I run the results, click OK, we should see that the deformations should be shown. Sorry about that. Program does not seem to want to cooperate with me today, which is very strange. Usually this all runs pretty smoothly. So while I'm restoring these, should be pretty quick. Again, sorry about that. Strange. All right, so let's go back to our nonlinear support and try running our results again. Okay, so this is what I was trying to show. So once our results have ran, you can see that I can show my support reactions here, turning on support reactions under the result navigator. And if I turn this into a wireframe view, you can see that our deformation on the right-hand side, so this support has fully failed because it's experiencing negative forces in the X direction. And you can see that if I go down here to static analysis and results by node in the table here, that under support forces, our node over here, node number 3, is experiencing negative support forces, and our node on the right hand side has no negative support forces, and that's because it's totally failed, and the cantilever is now pushed into the X direction where this support is supporting the cantilever at the top here, and so the deformation is not into the X direction. So yeah, that's how you can take into consideration nonlinearities for supports. We can move on to the next example, and this one is called ladder with friction support. And so with this example, you can see I have a ladder that I modeled here, and I created about 16 load cases here so that each load case has a point load on each rung of the ladder here. So, turning on my loads here, I can use these arrows right next to the drop down to go through, and you can see that each rung of the ladder has a point load of 1 kilonewton applied to it. And as I go through each of my load cases here, I'm going up the ladder here, and you can see, and the point of this example is to see at which height this load gets to, well, the friction that the ladder is using to being supported down here gives out. So you can see our supports down here are blue. And the reason they are blue is if I edit them, I've created some friction supports, which is another nonlinearity. So I turned on the nonlinearity for the translational X and Y directions, and the friction is based off of the vertical forces. And so turning on friction for each of these directions, you can see the 2 tabs up here. So UX, we can enter in a friction coefficient, mu x here, which is 0.2. And so this means that this support will fail if the force of 0.2 times the vertical force PZ is exceeded. So you can see that here in the graph. And so if I click OK, and we just go to our load case 1 here and run the results, and I click yes. So you can see that the bottom here, these supports are fully activated. And this is the deformation we would expect from our ladder here with our supports fully activated. These supports at the top here are just making sure, are acting as the wall that the ladder would be resting on. And you can also see I have my support reactions turned on here. So we're getting vertical reactions of 0.5 kilonewtons from our 1 kilonewton of loading. And then as we go up the ladder, we want to see at which point the supports will fail. So you can see as we go up the ladder that at about, once the loading gets to about this height here, we're at 0.08 kilonewtons. And you'll see that the maximum amount of force that these supports can take in the x direction is going to be 0.1 kilonewtons, because we want to multiply our mu, or friction coefficient, by 0.5, and that gives us 0.1. And so 0.1 is going to be the maximum amount of force that these supports are going to take in the x direction. So let's keep going. And then there is where you'll see that once this loading gets up to this height here, our supports, or our x direction forces, reach 0.1. And so our supports fail, and then our ladder gives out here. So that's how you can use nonlinear supports for friction supports. And so now we can move on to the next example. So the next example model is called tension specimen as surface model. And with this example, we have a specimen here of some sort, and this is similar to something you'd see in one of your labs. And this specimen here is made out of steel. And so we're just going to go over the general concept of plastic analysis. So the plastic deformation in a structural component, like I talked about earlier, is due to a load and is based on Hooke's law. And Hooke's law explains that the stress and strain relationship in most materials is linear and goes, most materials are a linear elastic material. So some examples you might want to take a look and see what happens after that linear elastic behavior happens of materials, and that's when we want to get into plastic analysis. So in this case, plastic behavior is what we want to take a look at. So RFEM 6 can consider nonlinear behaviors like this and take these into consideration. And to do this in RFEM, we have to go into the base data. So we can right click on our model here and go into base data. And so taking into doing plastic analysis, to take this into consideration, you have to, under the add-ons here, activate the add-on nonlinear material behavior. So this add-on is required. and this allows us to activate different material models. So let's click OK. And so now let's run the calculation on this surface just using a linear material model. So if I double click on this surface here, you can see I have two materials that I've already pre-made. So the first one here is a linear elastic material. And so we're going to choose this one. And you can see here I also have a plastic material or nonlinear plastic material that I've created. We're just going to take a look at the linear elastic one first. And I've also added in some loading here. So I'm just going to run the results so we can take a look at them. And here you can see the results. And so we can see the deformation here, but we can also take a look at the surface results and the stresses on the surface by going to surfaces, stresses, and then under equivalent stresses and under von Mises stresses, we can take a look at the von Mises stresses on the surface. And this is a kind of stress thesis that is known most commonly to be used for this kind of stress design for steel sections or surfaces. And so this test example has a yield strength of 260 newtons per cubic millimeter, or newtons per square millimeter. Sorry about that. So if I edit this material and I go to the material values, you can see down here the yield stress of this steel is 260 newtons per square millimeter. And so we can take a look at our control panel on the right hand side here. And so you can see we have our color panel here, and we can see exactly what the stresses are on our surface here. So the maximum amount of stress we're getting is 296 newtons per square millimeter at these dark red regions here. And this tensile stress should be only up to the yield strength in reality. We shouldn't be in reality seeing stresses on the surface here that are past the 260 newtons per square millimeter. So, and we can see the tensile line load that I've added here, and this force required to reach that maximum amount of force that this specimen can take before it reaches the yield strength is we have to take the yield strength of 260 newtons per cubic millimeter and multiply that by the area, the smallest area of our surface here. And so that would be 260 times 10 millimeters by 3 millimeters. And that'll give us 7,800 newtons. And so then we can take that tensile force and turn it into a line load by dividing it by the length of this line here, which is 14 millimeters. And then converting that, we get the value here of 557.14 kilonewtons per meter. And so that's the maximum amount of tensile force that this specimen should be able to take. So to see better results as well, we want to make sure that our results are set correctly. Our result smoothing is set correctly. So if we go to calculate here, we have some settings called result smoothing. And when you're looking at results like this, sorry, one second. sorry about that. When you're looking at results like this, you want to make sure that the option here, constant on elements, is set. So what this does is it shows the average value from the surrounding FE mesh points. And so there's no interpolation from the surrounding elements, which usually continuous within surface is set here by default. And so to get the most accurate results, you want to make sure that constant on elements is set when you're looking at stresses on a small surface like this. And so now we can see areas of the element here, like I said, which are higher than 260 newtons per cubic meter. And we can double click on our color scale here and set limits. So let's say I set a limit of 260. You'll see now all of the areas that are at that limit of 260 newtons per cubic millimeter, and then the areas that go above that limit or exceed it. So since this steel is an isotropic material, this, like I said, cannot happen in reality, and the limit can't be exceeded. But we are getting stresses higher than this. And so this is where we need to consider the material as a real nonlinear plastic material behavior. And we have to activate this using the add-on nonlinear material behavior and choose a different material. So let's double click on the surface here. And we can choose the material that I already have pre-made here, the second one. And we can also edit this material. So let's just take a look at the details of this material real quick. We can take a look at the different material models that are located here. So we have linear elastic, plastic for members, plastic for surfaces, and then a list of other nonlinear material models that you can choose from. We're using the isotropic plastics for surfaces and solids. Then choosing this will activate the tab up here, isotropic plastic for surfaces/solids. And so then under here, you can adjust the yield strength for tension and compression here individually. And you can set up here what hypothesis you want to view, or what the stress failure should be according to what hypothesis you want the stress failure to show using. We want to keep this set to the von Mises hypothesis for looking at those types of stresses. And so now we can click OK and click OK again. And our material changed, so we have to rerun our calculation. And so now you can see that if I set this color scale back, if we're looking at our surface stresses or von Mises stresses now, that we're not getting, that the highest stress shown here now is 260 newtons per square millimeter. So this is in reality what you would see. So you can see now that the material here is yielding, and we can look at criteria. We can turn on the criteria here, and this shows us exactly where the material is yielding basically, and going past the point where it can handle the stresses. And so this is what it looks like when you use a plastic material, and this is more accurate. And so we can also take a look at what happens if we increase our loading to something that's higher than what the yield strength is. And again, you can see if we look at our results here that we're also not getting anything higher than 260. and our material is yielding. And we can also take a look at our deformations. So you can see here what our deformations look like for right before the material yields. We're at 0.1 millimeters. So the material has not yielded or gone into the plastic region yet. And if we change this to load case 2, where we've gone past the limit of what the material should be able to handle, you can see now we're at 4.4 millimeters and the material has yielded. And you can see that in the neck here of the test specimen that it's thinning out. And we can also get a nice animation of what that looks like as well. So that's how you can utilize plastic materials in nonlinear effects in RFEM 6. And so this is very similar to what you should see in a lab experiment. And so our last two examples are going to be on singularities. So I'm going to go back to the PowerPoint and we are going to, okay, so sorry about that. Before we get into the next section of nonlinearities, we're going to take a break. But before the break, I just want to ask if there's any questions that were asked.
Yes.
Siska? Yeah.
Yes, hi, Alex. There's a couple of questions.
Okay.
The first one, at the beginning of the first couple models that you showed, you used a tension member for one of them, and then for the other one, you used the failure if compression for the nonlinearity.
Yeah.
Can you go over like what's the difference between the two options?
Yeah, I can do that. Yeah, so that first example, I did show for this member, for example, that you can set the member type to anything, and then you can check on the nonlinearity option. So for this example, the member type is set to truss, and this member type can take both tension and compression forces, but it can only take axial forces. But let's say I wanted it to not be able to take on compression forces. I can check on the nonlinearity option, have the nonlinearity tab come up, and I can add that to that member type. This would basically be the same thing, almost the same thing as just using the member type tension. And so with the member type tension here, this member type can only take tension forces and it cannot take compression forces, but it can also transfer moments and shear forces and not just axial forces. So that's the reason why I chose this nonlinear option here. But reality, they're both basically the same thing. So hopefully that answers that question.
Yes. And the second one, if we're able to import or export into AutoCAD, and where if you want to show them how to do that quickly.
Yeah. So just real quick, you can import and export back and forth between AutoCAD. So that would be, we do have direct integration with AutoCAD. So what you can do is go to File, and then you can go to Import, and then you can choose this option here, AutoCAD. And I don't have AutoCAD running right now, but if you did, a dialog box would pop up. And what you can do is you can only import and export lines between AutoCAD. You can also have information with these lines, such as cross sections and materials. So yeah, when you're importing and exporting between AutoCAD, things like surfaces and solids cannot be imported and exported between the two, but we do have that option. And you can also use the DXF file type as another way to communicate between AutoCAD and RFEM. So.
Okay, thank you. Yeah, that's all the two questions I have for you.
Okay, awesome. Thanks, Siska. Yeah, so let's take a 5-minute break, and then we can move on with the rest of the hour training and come back here around 3:06. All right, so let's resume. So next topic are singularities. So what are singularities and where do they occur? So singularities are points of discontinuity in the calculation model, and this happens in all FEA software. And this is where the results are not accurate and can't be trusted with singularities. And so what this means is that there isn't really any issue with how the software solves the model, and there's not really any physical issue with the model itself. So keep that in mind when it comes to singularities. Singularities can show themselves as infinite stresses or internal forces. And so with singularities, things like mesh refinement do not improve the result. Mesh refinement just only gives you a better idea of where singularities can occur. And singularities occur in FEA software when the loading or forces are all applied to only one single finite element node. And so the typical singularity locations are usually point and line loads and supports. And the solution to this would be something that I will show you on how to avoid these in the next RFEM example. They can also occur at openings and re-entrant corners. And to solve this issue would be to add in some rounded corners instead. And they can also occur at stiffness changes due to the changing in material or thickness, or drastic changes in material or thickness. And so the solution to this would be to possibly space out smaller changes in thicknesses using something like steps. And so now let's go back to RFEM and model an example to show this. So I'm going to create a new model, and I'm going to give this model a name. So it's going to be singularity point load 4. And I'm going to keep all of these settings same, and I'm going to deactivate the load wizard and combination wizard under the second tab here. So then I'm going to click OK again, and this will create the blank model here. And very similar to the first model we created, I'm going to go up here to the toolbar and choose the tool New Rectangular Surface. And again, I'm going to create a new thickness because every surface needs to have a thickness of material to it. I'm going to just simply use concrete 4000 psi. Click OK. And the thickness is going to be 12 inches. Then I'm going to click OK and click OK again. And then I'm going to draw my rectangular surface here and make it 32 feet by 16 feet. Right click to exit out of that tool. And now we have our rectangular surface created. So the next thing I want to do is add a node to the center of my rectangular surface here. So I'm going to go up here to node in between two nodes. And what this would allow me to do is to choose two nodes here, and it'll place a node in the center once I click apply, which you can see there. And I can exit out of that. And now I have a node placed at the center of my surface here. And what I want to do is add a new nodal load to that node. And this nodal load is going to have a force magnitude of -10 kips. It's going to be applied as a force in the z direction. So I'm going to click OK, choose that node, and click OK again. And now I have a load of -10 kips applied to the center there. And now we have our surface loaded, we need to support it. So I'm going to just support the boundary lines of this surface. So I'm going to go up here to assign line support and just choose the hinged predefinition support here. Click OK. And then I can simply just highlight the entire surface here. And that will add in my line supports to my boundary lines. So then I want to make a copy of this. So I'm going to highlight everything and use the move/copy tool and create a copy. And I want to create 3 copies. And these are going to be in the X direction, 37 feet, or displaced in the X direction, 37 feet, like so. And so now that we have our copies made, we can then create our 4 mesh refinements like we've done before. So we can go under types for surfaces, surface mesh refinements, right click on that and click on new surface mesh refinement. And then our first mesh refinement here is going to be 7 feet, and we're just going to make 3 copies of that. And it's going to be 4 feet for our second one, 1.25 feet for our third one, and 0.4 feet for the fourth one. And then we can, instead of just assigning these graphically, if we know our surface numbers, we can simply just type that in. So for the 7-foot one, I'm going to type in 1. For the 4-foot one, I'm going to type in 2. 3-foot would be 3, and the 0.4 feet would be 4, surface 4. Click OK. And now you can see those symbols for our FE mesh refinements on each surface there. And turn off my grid. And then we also want to add in a results section similar to last time. So I'm going to create a results section using 2 points. So again, this dialog box will pop up for results sections. You can just click on this button here, select 2 points in graphics. Type here 2 points in a vector. And that vector is in the global z direction and the local z direction, positive z direction. So we'll click OK, and now we have our section cut there for our results. And we also have our LC1 that was created here. So if I edit that, we can turn off self-weight for our load case there. And then we can simply hit calculate and run our calculation. So now we have our results sections activated, which you can see here. What I want to do is under results sections, turn on local extremes. And so now you can see we have our local extremes for our deformations turned on. We can also shrink the size of our loading there, or our load. We can turn this off. And right now we're looking at our global deformations, which they look okay. They look good. Doing a quick visible check here, and this is what you would expect from our global deformations. Let's take a look at our internal forces. So if we go to internal forces and we take a look at our bending moments along the x-axis here, this is where things start to get a little tricky, because you can see here our surface on the left here is showing a maximum moment of negative 2.91 kip feet per foot. And then our last surface here is showing a very different number of negative 5.5. And so we know that the finer the FE mesh, the better than the finer FE mesh here is better than the coarse FE mesh. But the question is, which moment is the right moment here between these surfaces? And the answer is that none of them are correct. None of these surfaces are showing the correct moment that we would expect to see in reality. And this is because of singularity. And so the results aren't useful here. We can't use these results. And it doesn't matter what the size of the FE mesh is, because we have a singularity occurring, which you can see if I zoom in here. This is what you would see from a singularity. And the reason we're getting a singularity is because we applied a nodal load or a single point load, which is just feeding into one single FE mesh point. And so the solution to this would be to take this one single point here and distribute the nodal load over the surface instead of into a single load. So what we want to do is create a surface load. So we're going to take this load and divide it by a random surface area. So I'm just going to take this load and delete it. And we're going to take this 10 kips and divide it by 2 square foot. So to apply this new surface load, we want to create a new load case. And this is going to be a regular load. And this new, so we're going to go up here and actually I'm going to undo this. Yeah, so we want to create a new load case. This one's going to be called regular load. This one was our point load. Going to click OK. So now this regular load, we're going to use the tool under this tool here. So I'm going to hit the drop down next to new free rectangular load. Sorry about that. So under here, we're going to go to new free rectangular load and choose that. And this is going to have, first we're going to choose load distribution as uniform. And this is going to have a magnitude of negative 5 KSF. And we want to choose the load location as center and sides of rectangle. And this rectangle, or the size of this rectangle, is going to be equal to 2 square feet. So that's 1.41 for each side. And our load is going to act on the XY plane and in the global Z direction. And then we just need to choose a center for it. So we can choose that graphically by clicking this button and choosing that node in the center. And then we also need to assign a surface, so we can choose that graphically as well, like so. And so now if we just hit the button here apply and next, you can see that that loading has been applied. And now we can do the same thing for the rest of our surfaces, or we can exit out and then we can just take this load, hold Control, and we can simply hold Control, drag and drop our load to each next surface there. So now we have our loading distributed more. And so now let's run our calculation. And so now we should see, actually, so I made a mistake. We're not seeing results on these surfaces because we need to set assign to surfaces to all. So double clicking on one of these loads and just changing it. Actually, sorry about that. We want to highlight all of these loads here and double click on them. And we need to make sure this assigned surface here is changed to all. So it looks like we can't do that for multiple loads. Just want to do that for one load each time. Yes. And we want to do that for the last two here. And that is the reason why we weren't seeing any results there. So let's try running our results again. And so now we're seeing more consistent moments between each of our surfaces here, and that's because we don't have any singularities on every surface, showing we have more similar moments. And this is one way to fix singularities, is having the loading distributed over multiple FE mesh nodes instead of just feeding into one singular node. And we can compare this again to the singularity that we actually had in the first load case. So now we can also, if this occurs, we can also, instead of doing this, to fix the singularity, we could look at our result diagram for the section cut we have here. So if I right click on the section cut and go to result diagrams, we can go to, you can see here our singularity. And what we can do is use a tool called result smoothing. So I can click on this button, edit smooth ranges. The tool is called smooth ranges. We can use this tool to add in a smooth range, which averages out the results. So let's say, for example, we want this smooth range to occur right on the last surface where the singularity occurs, which is 111.295 feet, and it ends at 112.705, and this is the size of, you'll see 1.41 feet, which is the size of our column that we're pretending is connecting into this element. And so we'll click OK. And now you can see we have this smooth range up here. You can see we have the averaged out results down here at the bottom. So you can move this range around, and you can use this to smooth out the singularity here. I'm not sure why this region is, the values here are a little hard to see for some reason. They're grayed out, but you can see them here on this example. So this 3.213 is the smoothed out region there. But that's how you can use smooth regions or smooth ranges to cancel out singularities when looking at the result diagram. It should look something like this, these results here. So that's how you can use smooth ranges, and you can take this range and you can move it around as well, like so. And you can see the results that it's changing. So if we exit out of that result diagram, we can move on to the last example. So I'm going to open up a new model. And this model name is going to be singularity, similar to the other one. And it's going to dash nodal support, and add a 4 after that. So that's our model name. We'll keep the model type as 3D, and everything else we can leave the same. Under the add-ons tab again, I'm going to deactivate the load wizard and combination wizard, as we're not going to be automatically generating load combinations for this model. So we'll click OK. And now again, similar to the other model, we want to just create our 4 surfaces again. So I'm going to go up here to new rectangular surface, and you can see some of my previous thicknesses have carried over, but I'm going to create a new thickness again by clicking on this button. And then the material, again, I'm just going to choose concrete 4000 PSI. And something else to mention in the material library is if you're not located in the United States, we also have a long list of other countries here and other standards that you can choose from. So always good to know, but that's how the filter works on the left-hand side here. So again, we'll choose 4000 PSI, click OK, and then enter in a thickness of 12 inches again. And then we can go and proceed with drawing the plate here, which will be 32 feet by 16 feet. And then we want to model and add in supports. So this line on the right-hand side here is going to be a line support with hinges. So I'll click OK and graphically select that line and add in our hinged line support there. And then I'm just going to create a new standard node. And I'm just going to place this pretty much anywhere in this region, like so. So now we have a node integrated into our surface here automatically. And I'm going to assign a nodal support to this node, just a normal hinged nodal support like so. And then I'm going to add in a surface load. So I'm going to create a new surface load. And this is going to be just another load, 210 pounds per square foot. And I'm going to click OK and apply that graphically like so. And again, we can shrink this load. And also we want to edit our load case here, and again, turn off self-weight. For our load case, we don't want to take into consideration self-weight. And we also, again, want to create some surface mesh refinements just to see the difference. So we'll create a new surface mesh refinement. And this first one again is going to be 7 feet, and then 4 feet, and then 1.25 feet, and then 0.4 feet. And then we can add and assign our surfaces. So 1, 2, oh, wait. Oops, we didn't create our copy. So I'm going to click OK. And we need to create a copy of our surface here. Forgot to make our copy. So highlight that and go up here to the move/copy tool. Click on that. We want to create a copy, create 3 copies. These are going to be displaced 37 feet, again in the X direction. Click OK. Now we have our copy there, and we want to, then we can just assign our mesh refinements graphically by right-clicking on them, selecting the desired surface. So we'll assign those graphically. And yeah, once we have those assigned graphically like so, we can add in our result, our new section result, by choosing 2 points graphically. And so we'll choose our 2 points again. Click OK. And now that we have our section cut here, and we have our loading applied, we can run our calculation. And so once we run our calculation, I can turn the loading off and the results sections off. And we can see what our deformations look like. So they look pretty good. That's what I would expect from this setup we have here. But what we want to see is the singularities at these nodal supports. So all of the loading right now, if we check on surface results, and then we check on MX, and we turn on our results sections, all of the loading that's applied to the surfaces here has all been fed into the single nodal support. So if I turn on local extremes, you can see that at that single nodal support, all of the loading is being fed into there. And we are getting super high moments at those locations because that nodal support is just sitting on one single FE element. So that's what the singularity looks like for something like a nodal support just feeding into one FE mesh node, and something you really need to look out for. So these are not results you can rely on, and the correct result out of all of these surfaces is none of them. None of these are correct, and it doesn't matter what your FE mesh looks like. But like I mentioned before in the PowerPoint, having FE mesh, having a finer FE mesh doesn't fix singularities, but it does, as you can see, give you a better idea of where that singularity is exactly located. As with this, you have no really clue where that singularity is happening. You just have a better idea with this finer mesh here. So the solution to this problem is, like I mentioned before, you could use the smooth ranges to solve this issue. So if we right click on the section here, you could add in a smooth range here and smooth out the results here and get a better idea of what the results should be there. And that range would be the length of whatever element is connecting into the surface here at this, what this node's supposed to be representing. Or you can change your supports from something infinitely rigid, like what these are set to now, to something that that is less stiff. So the stiffer the element, the more loads they attract. And so caution should be used when it comes to fully rigid nodes like these. And what we could do is we could edit these nodes. Editing just one of the node will edit all of them because we're using the same nodal support definition for all of them. So if we go over here to edit and we check on stiffness via fictitious column, this is an option down here. So, I mean, what you could do, so these are all, when a degree of freedom here is checked on for either translation or rotation, that means that degree of freedom is fully fixed. So all translational degrees of freedom here are fully fixed, and only the rotational degree of freedom here, Z, is fully fixed. Phi Y and Phi X is fully released. But you can see when you fully release something, you can add in a spring constant, so it's semi-rigid based on the spring constant you have added in here. So when I say to make something less rigid, you could add in a spring constant, or like I was about to mention, for this example, we're assuming that a column is feeding into the surfaces, so we can use a stiffness via fictitious column, this option here. And when I check on this option, you can see that this tab up here, stiffness via fictitious column, has popped up. And what this allows us to do is gives us some parameters here. So under model of supported by, we can choose between elastic surface foundations, elastic nodal support, or nodal support via adapted FE mesh. We just want to focus on the option here, elastic surface foundations. And then the column head is rectangular, and the dimensions of this column, we're assuming, again, the column has an area of 2 square feet. So the dimensions would be 1.41 feet by 1.41 feet. And then we're assuming the column has a height of 10 feet. And so once we enter that information in, we don't need to worry about the rest of this. Well, we do need to enter in a column material, so we can choose our surface material, which is 4,000 psi, and the column section, just going to, keep this same as column head. So the whole section is 1 foot or 1.41 feet by 1.41 feet. And so once we enter in this information, we're also assuming the base of the column is hinged, the boundary condition here. What this all does is feeds into a calculation, and RFEM will calculate for you what the spring stiffness spring constants are for this column. And it will take these spring constants and will apply them to all of our degrees of freedom for us. So now this nodal support that we have applied, which you can see in the graphic here, at each of our surface is now a spring, which you can see denoted by this symbol here. And so if we click OK, click yes, click OK again, now you can see that each node here is a spring, and these nodes are no longer fully rigid. So what we can do now is run our calculation again. And so now we should see We can look at our global deformation. Not much has changed there, probably just the amount of deformation. But looking at our surface results, we can see that we have now more consistent results. They're a little different from each plate, but now they're more consistent. And to even increase these results more at these locations, there's not only just surface refinements that you can add, but you can also add FE mesh node refinements to each node here. So if you want to add those, you can right click on the node and you can go under assignment and click on nodal mesh refinements assignment. And we can click on new nodal mesh refinement. And you can see this graphic here showing you what this refinement is going to look like on the node. So basically, you can choose a circular refinement or a rectangular. We're going to use circular. And the radius of this refinement is going to be 5 feet. The inner refinement is going to be 0.33 feet. And the outer refinement is going to be 1 foot. And so once we click OK, yes, and click OK again. Now it might be a little hard for you to see, but there is this sphere looking symbol telling me that there's an FE mesh node refinement at this node here. And what I can do is I can hold Control and drag and copy this refinement to each of my nodes, holding Control, left clicking and dragging. And now when I run the results, you can see what the FE mesh looks like. So now that we have that at each surface, the FE mesh is the same for each surface here. You can see our results are basically the same now at each surface. And even though you can see the opening here is resembling what the column would look like on the surface from our fictitious column that we added with this node, even though we did that, you can still see that we have somewhat of a singularity occurring at this location here near the column edge. And this is another point where you would want to basically just take note of this location where the singularity is occurring and make sure to take these, just make note and take this into consideration for when you're doing design work on a surface and see something like this. So just important to notice things like this. So that's the end of my singularity examples there. And now I'd just like to give another test. So I'm going to open that up now. Launch that. And if you guys could answer this test, then we can move on and go over it. All right, so looks like mostly everyone answered. So I'm going to close this question or poll. We can go over the answer. So I'm going to share the results. All right, so the question is, where do singularities occur? And the correct options, or okay, let's go over the options first. So the first option was point bearings or load application. So that was like the nodal load that we added. Corners of walls, which we didn't go over, but I did mention. Jumps in stiffness or drastic changes in material or thickness, and then the last option was beginning and ending of line supports. So all of these options were correct. Yeah, point bearing and load application is the nodal load that I added in the second to last example we did, which can cause a singularity. Corners of walls, this is similar to also the beginning and end of line supports. So whenever you have a corner, let's say, of a wall feeding into a surface. So let's say, for example, I want to change my work plane here to there, and I also want to move it over a little bit, like that. So you can change your work plane, your grid work plane, using these buttons up here, and you can change the origin of the grid work plane using this button. And let's say I have a wall that I just drew in here that's supporting this surface like this, like so. So whenever you have a wall feeding into another surface, or like a slab resting or bearing onto a wall like this, let's just say I get rid of this nodal support. We have a load applied to here. Actually, this would probably be better if I just took this and placed it. Yeah. All right, let's take this, just move it over like so. Okay. And I just changed my grid, my origin here like that. And yeah, let's just redraw that wall on this like that. Okay, so if we had a wall bearing down, or a slab bearing down on a wall like this, let's see what it looks like. So this is basically what I mean when oh, we don't have it supported. I delete this. We need to add in a line support like that to this wall. Let's try that again. Definitely gonna be, there we go. So yeah, when I mention, or that question when it talks about corners of walls, so you can see right here where this corner of this wall feeds in to this surface here is where another singularity can occur, like that, at this point here. So when I talk about corners of walls, you want to watch out for this, and what you can do is, adding an FE mesh refinement like this would help, but it would also help to just make the corner of this wall rounded just a little bit, so it's not just one single point feeding into an FE mesh node like that. And then also we have regions, smoothing regions that you can apply to your surfaces here as well. And that is also another way to combat a singularity like this. So I'm not sure at the moment where the smoothing region is located, but I know we do have them. So yeah, that's what happens. That's another cause of singularities. And then the last option that was in that question, beginning and end of line supports. That's similar to a wall like this. Let's say you have a line support just like representing this wall. You can also get singularities at the beginning and end of a line support. So that is the end of the examples that I have planned for today. Siska, I don't know if there's any outstanding complex questions you couldn't answer that we could go over.
Hey, Alex. No, just a simple one. Can you just go over how to turn on and off the mesh on this surface?
Yeah. So do you mean turning it on and off graphically?
Yes. Yeah,
Okay.
like the squares that's shown right there if you don't want to see that.
Yeah. So if you don't want to see if you want to get a cleaner view of your model and you don't want to see the FE mesh here, you can go up here to this drop down next to the button and you can turn off the display of your FE mesh like so.
Okay.
Yep.
That works. And the other one is it possible to design weld in RFEM?
Yeah. So weld design is possible in RFM. Let's say these two surfaces here are steel surfaces and you wanted to design the weld that's connecting these two surfaces. What you would need to do is go up to the base data and the model, and under add-ons we have a design add-on that is called stress and strain analysis. And what this stress and strain analysis add-on does is it releases stresses into the program so you can view stresses on things like members or elements like members. That's what it does, is it gives you the ability to view stresses on members. And so if I click OK, you can see now in this add-on here, or in the table, if I go under the drop-down, the stress strain analysis add-on is available here. And basically what this does is it allows you to just run a simple stress analysis comparing the design stresses to the limit stresses of something like a surface or a member. But what it also does is if I right click on this line here and I go to edit the line, you can also activate the option here, welded joints for a line. And then you can design the weld for a line like so by creating a new welded joint. And you can see we have a bunch of joint types and weld types, and you can enter in the settings and parameters for that. So that's how you can design a welded joint. You can see here you can choose the line and the surfaces that are jointed together. So yeah.
Thanks, Alex. That's all the questions I have for today.
All right, awesome. Thank you, Siska. So with that said, this is the end of our training. So I just want to point out some free online services we also have on our website, which you can see here. I encourage you to visit our website if you're looking for some FAQ and knowledge base articles. We also have models that are free to download. And I also recommend checking out our YouTube channel for more webinars and videos. If you're a student, you get a free student license, which you can fill out a form on our website to apply for this. All you need to do is show a transcript or proof of enrollment. And also our e-learning videos for students are very beneficial, I think. And we also offer free support via email and chat. You can see here our email is info-us@doolittle.com. So if you have any questions at all about your model, if you have an instability with a model, or you have questions about modeling, you can email this email, and we have a pretty quick response time. And you can also send in a model, and we can take a look at it for you. You can also call us at 267-702-2815. And again, I just want to thank everybody for attending. Hopefully you found this training beneficial. Thank you, Siska, for moderating. Any training materials such as the recording, PowerPoint, and models will be sent out in the next couple of days. And if you could take a couple minutes after the webinar ends to fill out our evaluation form that will pop up when this webinar or when this training ends, that would be much appreciated if you could let us know how the training was for you and if there's anything you liked or didn't like. And yeah, thanks everyone. So I hope you have a good rest of your week. And if you're in America, don't forget to vote. So thank you.